Our dynamic universe. The key areas covered will be resolving the weight of an object on a slope into a component acting down the slope and a component acting normal to the slope. Systems of balanced forces with forces acting in two dimensions. What we will do today is investigate forces involved when an object slides down a slope and carry out calculations on the above. Forces acting down a slope. If an object is placed on a slope, then its weight acts vertically downwards. A certain component of this will act down the slope. The weight can be split into two components at right angles to each other, and we can say that the component of weight acting down the slope is F equals mg sine theta. Here's a little diagram we've got where the component of weight down the slope is mg sine theta, and the component of weight perpendicular to the slope is mg cos theta. A block of wood of mass 2 kilograms is placed on a slope which makes an angle of 30 degrees with the horizontal. If a frictional force of 4 newtons acts on the block, what is the unbalanced force down the slope? Well, let's draw a little diagram first. We have our slope, we have the horizontal, we have our block. We know that the weight acts vertically downwards, so that's our W, and remembering W equals mg. And our component of the weight acting down the slope, let's label that W and then down the slope. We know that our equation for the weight down the slope is equal to mg sine theta. So we can put some numbers in here. Our mass in the question is this 2 kilograms just here. G we know is 9.8. If we can't remember that, it's in your data sheet. And sine theta, remember we can add that 30 degrees into there. So we've got sine of 30. If we put this all into a calculator, we get 9.8 newtons. Now we want to work out the unbalanced force down the slope. We have our unbalanced force is equal to the weight down the slope minus friction. Remember, we need to include this friction in here. So the weight down the slope minus friction, as they're acting in opposite directions. So that's equal to 9.8 minus 4, so our final answer is 5.8 newtons. A van of mass 2,600 kilograms moves down a slope which is inclined at 12 degrees to the horizontal as shown. A. Calculate the component of the van's weight parallel to the slope, and B. A constant frictional force of 1,400 newtons acts on the van as it moves down the slope. Calculate the acceleration of the van. We have a part C on here, which is calculating the kinetic energy of the van, and that will be covered in a further PowerPoint. So looking at part A, we want to calculate the component of the van's weight parallel to the slope. We know that the component of the weight down the slope, so this just here, is mg sine theta. I'm going to label this as WP to save out writing it every time. And we have our W just here, which is equal to mg. So our weight parallel to the slope is equal to mg sine theta. We've got our mass in the question there, that's 2,600 kilograms, and we have our slope, which is at 12 degrees, so we can put these numbers in. 2,600 times by 9.8, which are g, and times by sine of 12. This gives us an answer of 5,298 newtons. Let's look at B. A constant frictional force of 1,400 newtons acts on the van as it moves down the slope. Calculate the acceleration of the van. We know that we can use the equation of our unbalanced force equals mass times acceleration to work out acceleration, but we need to work out our unbalanced force first. Our unbalanced force is going to equal our weight perpendicular to the slope, sorry, not perpendicular, parallel to the slope, minus our friction. Again, because they're acting in opposite directions. So we worked out our weight parallel to the slope as 5,298. Take away friction, that is given in the question there, 1,400. And we get an answer of 3,898 newtons. Now we can go back to our unbalanced force equaling mass times acceleration. So 3,898 equals our mass is up here, that's 2,600, multiplied by our acceleration. Rearrange this. 3,898 divided by 2,600 gives us a final answer of 1.5 meters per second squared. And part C, already mentioned that this will be covered later in the course. A fairground ride consists of rafts which slide down a slope into water. The slope is at an angle of 22 degrees to the horizontal. Each raft has a mass of 8 kilograms. The length of the slope is 50 meters. A child of mass 52 kilograms sits in a raft at the top of the slope. The raft is released from rest. The child and raft slide together down the slope into the water. The force of friction between the raft and the slope remains constant at 180 newtons. We've got quite a few parts to this question, so let's just take them one at a time. Part A. Calculate the component of weight in newtons of the child and raft down the slope. So we know the equation we want to use is our weight down the slope is equal to mg sine theta, just like we've been using before. Looking for our numbers, we have our mass. We've got a child of mass 52 kilograms, and we have a raft of mass 8 kilograms. So we're going to have to add those together. That's the combined weight. We have g, we know that's 9.8, and our theta is 22 degrees to the horizontal just there. So 52 plus 8 there, multiplied by 9.8, multiplied by sine of 22. Popping this all into a calculator is going to give us 220 newtons. Part B. Show by calculation that the acceleration of the child and raft down the slope is 0.67 meters per second squared. If we want to calculate acceleration, we want to go back to our unbalanced force equals mass times acceleration equation, but we need to know our unbalanced force. Looking at our question, we can see that we've got a frictional force there. So our unbalanced force is going to equal our weight down the slope minus the friction. This is equal to, what did we get last time? We got 220 minus 180. That gives us 40 newtons. Now we can say our unbalanced force is equal to mass times acceleration. So 40 equals our mass, again, that's this 52 plus the 8, which is 60, multiplied by the acceleration. Acceleration is 40 divided by 60, that's just rearranging this, and this gives us 0.67 meters per second squared. And this is exactly what they wanted us to find out in the question. That matches up perfectly. Part C. Calculate the speed of the child and raft at the bottom of the slope. We want to go back to our equations of motion for this, so writing down our suvat, we know that the displacement, we can see up at the top of the question here, the length of the slope is 50 meters, so that's how far the child travels, so 50 meters. Our initial velocity, we can see in the question, the raft is released from rest, so our initial velocity is going to be 0. Our final velocity is what we want to work out, because we want to calculate the speed of the child and raft at the bottom of the slope. Our acceleration, we've just worked that out and it's given in part B, that's 0.67 meters per second squared, and we don't know our time. So if we want to work out our final velocity, but without using time, the equation we want to use is v squared equals u squared plus 2as. Plugging our numbers in, we've got v squared equals 0 squared plus 2 times 0.67 times by 50. V squared is equal to 67, and so the square root of 67 is 8.2 meters per second. And that's our final answer there. Part D. A second child of smaller mass is released from rest in an identical raft at the same starting point. The force of friction is the same as before. How does the speed of this child and raft at the bottom of the slope compare to the answer to part C? Justify your answer. Thinking about this one, let's have a little look at the equations we used. First one, to calculate the unbalanced force, we used our component of the weight down the slope, and that was equal to mg sine theta. And we combined that with friction to get our unbalanced force. So our unbalanced force was equal to the component of the weight down the slope minus friction. This was also equal to mass times our acceleration, and then the last equation we used was v squared equals u squared plus 2as, and that was to get our speed of the child at the bottom of the slope. So having a little look at our first equation, the only thing that decreased on the right hand side of this equation was the mass. We know our gravity stayed the same, we know that the slope stayed the same. This mass decreased. Therefore, to keep the equation balanced, our component of the weight down the slope must also have decreased. So that can be our first little bullet point that we write. The component of weight down the slope decreased. Then let's have a look at our second equation we used. This was the unbalanced force equals the component of the weight down the slope minus friction. If our component of the weight down the slope decreases, then that means our unbalanced force is also going to decrease just there. This is because our friction is staying the same, as it's the same raft that's being used. So our next little sentence can be our unbalanced force decreases. Looking at our next equation, if our unbalanced force is decreasing and our mass is decreasing, then to keep that equation balanced, our acceleration must also decrease. So there we go, third little bullet point. The acceleration of the child and raft decreases. And lastly, if our acceleration is decreasing, that's this just here, our displacement is staying the same and our initial speed is staying the same. To keep that equation balanced, our final speed must decrease. So that's our final little bullet point there. The speed decreases.